Hello everyone, and welcome to the Panthera-HT 6-axis robotic arm quick start tutorial series. In this series, we'll take you through everything from scratch, a step-by-step guide to getting started with the Panthera-HT 6-axis robotic arm. This series is designed for beginners with no prior robotics arm development experience. We'll walk you through environment setup, basic control, and hands-on examples in the order you'd actually follow during setup and verification. Each episode comes with written documentation and reusable code, so even without any prior ARM development background, you'll be able to unbox, get running, and make real progress from 0 to 1. All materials are shared through a GitHub repository, with equal emphasis on hands-on practice and conceptual understanding. Let's get started. Okay, so today is episode 1, SDK Quick Start. We'll walk you through environment configuration together, cover the core APIs in the SDK, and run through a few practical code examples to show you how to operate the arms hands-on. Let's first walk through the main files. Inside the SDK directory, open the description folder under Panthera's Python, then open URDF. This is where the robotic arms URDF mono files live. You'll find two URDF files, one for the follower and one for the leader. The content inside is identical. They're kept separate to make it easier to distinguish roles in leader-follower teleoperation tasks. Next, go into the robot param directory. This contains the parameter configurations for the arm body and motors. Open the follower point YAML here. You'll find settings like joint direction limits and maximum torque. Feel free to explore these in detail on your own. One important thing to note, the joint names defined in the URDF must exactly match those in the configuration file. Otherwise, features like forward and inverse kinematics will not work correctly. The config file points to the underlying motor parameters and the URDF path. Next is the scripts folder. This is where all our runnable examples are stored. Motor example contains low-level motor routines, which you generally won't use directly. Panthera-lib is the packaged high-level library that all the upper-level examples depend on. Now cd into Panthera Python directory in your terminal, then open the README file. We'll start by creating and activating a virtual environment using Conda. About the installation of Conda, you can find a lot of tutorials on the internet. I'm running Ubuntu 22.04, so I'll install the motor SDK using a pre-compiled package. Just select the package matching your Python version. If you're not on Ubuntu 22, use method 2 and build from source. Here we can see it's successfully installed. And install the remaining dependencies. Installation complete. You can now manually verify the installation. If your output matches mine, then your environment is set up successfully. Power on the robotic arm, then check the connected serial port devices. You should normally see 7 ports listed. Grant permissions to the serial ports. After unboxing, you'll need to manually adjust 2 joints to their 0 positions. Before running anything for the first time, execute the joint state readout script to verify the connection between your computer and the arm. cd into the scripts directory and run the script. If the connection is healthy, you'll see the port number, motor IDs, and initialization info. The terminal will then continuously print each joint's position, velocity, and other state data in a loop. Try moving the arm manually and watch the values change. Open the Panthera.py file. This is where all the main API interfaces are defined. The robotic arm is encapsulated as a class. Just instantiate an object to get started. If you have your own parameter file, pass it in via config path. It defaults to none. For state readout, you can use these get methods to retrieve the position, velocity, and torque state of each joint, as well as various states of the gripper. On the control side, there's joint position velocity control with maximum torque, joint velocity control, Cartesian space motion control, and many more. Feel free to explore them. There are also methods for forward and inverse kinematics computation, including Jacobian and gravity compensation functions. Now let's run a few example scripts to see them in action. The first is 6-joint position velocity control. You pass in 3 target positions, and the arm will reach each one in sequence at a specified speed, then return to the 0 position. The second is 6-joint PD control. PD control is the foundation of many control strategies, impedance control and trajectory tracking, both built on this approach. The terminal will print each joint's position, velocity, and torque state in real time. When the arm is powered off, it enters damping mode and slowly descends in order to protect both the motors and the operator. The third is gravity compensation. In this mode, you can freely move the arm by hand. By computing the compensation torque in real time, the arm continuously applies an upward supporting torque to counteract gravity, allowing it to hold any position you place it in. And finally, the Cartesian space keyboard control program. Use WASD to move forward, back, left, and right, Q and E to move up and down along the Z-axis, and the numpad keys 1 through 6 to rotate around the X, Y, and Z axis. When you close the program, the arm automatically returns to the 0 position. In this episode, we completed environment setup and installation verification, got an initial look at the core APIs, and successfully ran 4 key scripts: position velocity control, PD control, gravity compensation, and keyboard control. There are many more example scripts in the directory, including forward and inverse kinematics, impedance control, and teach and replay, covering everything from basic joint control to advanced Cartesian space control, from point-to-point motion to complex trajectory tracking. Feel free to explore based on your own needs. In the next episode, we'll demonstrate drag and teach trajectory replay to pick up objects, show a dual-arm leader-follower teleoperation setup, and walk through the APIs behind these features, so you can see the arm in action in more flexible, real-world scenarios.